Hello, I'm Liao. Welcome back to Evan of Code 2023. We are solving programming puzzles every day and we are on day 12. So what's the challenge for day 12? Let's take a look. Day 12, hot springs. You finally reached the hot springs. You can see steam rising from secluded areas attached to the primary ornate building. As you turn to enter, the researcher stops you. Wait, I thought you were looking for the hot springs, weren't you? You indicate that this definitely looks like hot springs to you. Oh sorry, common mistake. This is actually the onsen. The hot springs are next door. You look in the direction the researcher is pointing and suddenly notice the massive metal helixes towering overhead. This way. It only takes you a few more steps to reach the main gate of the massive fenced-off areas containing the springs. You go through the gates and into the small administrative building. Hello, what brings you to the hot springs today? Sorry, they are not very hot right now. We're having a lava shortage at the moment. You asked about the missing machine parts for Desert Island. Oh, all of Gear Island is currently offline. Nothing is being manufactured at the moment, not until we get more lava to heat our forges and our springs. The springs aren't very springly unless they are hot. Say, could you go up and see why the lava stops flowing? The springs are too cold for normal operation, but we should be able to find one springy enough to launch you up there. There's just one problem. Many of the springs have fallen into disrepair, so they are not actually sure which springs would be even safe to use. Worse yet, the condition records of which springs are damaged, which is your puzzle input, are also damaged. You'll need to help them repair the damaged records. In the giant field just outside, the springs are arranged into rows. For each row, the condition records shows every spring and whether it is operational, which is a period, damage, which is a hash, and this is part of the condition records that is itself damaged. For some springs, it's simply unknown, which is question mark, whether the spring is operational or damaged. However, the engineer that produced the condition records also duplicated some of this information into different formats. After the list of springs for a given row, the size of each contiguous of damaged springs is listed in order of those groups appear in the row. This list always accounts for every damaged springs, and each number is the entire size of its contiguous groups. That is, groups are always separated by at least one operational spring. So 4 of a hash would always be 4, never 2, 2. So condition records with no unknown spring conditions might look like this. Okay, so this is the condition records. However, the condition records are partially damaged. Some of the springs condition are actually unknown. So this condition is like 1, 1 and 3, right? So this is 1, 1, 3. This is 1 and this is 6 and this is 5, so it's 1, 6, 5. However, some of them is actually question marks like this. Right, so equipped with this information, it is your job to figure out how many different arrangement of operational and broken springs fit the given criteria in each row. For this first line, there's exactly one way to separate groups of 1, 1 and 3 broken springs in that order can appear in that row. The first 3 unknown springs must be broken, operational and then broken. So this, to make this whole row this situation. And the second line is more interesting. This 1, 1, 3 could be a total of 4 different arrangements. The last, this question mark, must always be broken because this has to be 3 to satisfy the final contiguous group of 3 broken springs. And each question mark must hide exactly one of the 2 broken springs. Neither question mark could be both broken springs, or they would form a single contiguous group of 2. If that were true, the numbers afterward would have been 2, 3 instead. Right? So this has to be broken, broken operational, or broken operational, broken, broken operational, operational, broken, broken operational, right? So it can be either this or this, so there's total 4 possible arrangement of each spring. Because last line is actually consistent with 10 different arrangements, right? So this, that will be actually the last one. This one will have 10 different arrangements. Because the first number is 3, the first and second question mark must be both a period, and like this, okay? However, the remaining run of unknown spring conditions can have many different ways they could hold groups of 2 and 1 broken springs. All these different combinations. In this example, the number of possible arrangements for each row is like this. Adding all of the possible arrangements count together produces a total of 21 arrangements. For each row, count all of the different arrangements of operational and broken springs that meet the requirement given the criteria, and what is the sum of those counts. So that will be our puzzle. So now we know this question, and let's take a look at how we can solve this. So let's start with open up our code editor. I'm gonna create a new file called day12 puzzle1. So you can see that here that all the puzzles that we have done over the past 11 days are all in here, and I've pushed this code into the GitHub, and so you can actually find this code in the link to all this code in the description below. Alright, so the first thing, as we always do, is we are going to copy the puzzle input. Here we're going to copy a simple one. This is a simpler puzzle input. Okay, before and to try our logic before I actually try out the actual puzzle input. So I've copied the input. I'm gonna create a variable called input. I'm gonna paste this puzzle input here. So for this input, first thing is we're gonna split by every line, and every line we're gonna find out how many arrangements we can get, and then we add up the sum. So first thing is we have a sum. And then last thing we're going to do is going to print out the value of the sum. And for every line of input.split line, we're going to calculate the number of arrangements that we can make for this line. Right? So for the line, after we split the input by new line, we get one line, which is this line, and we're going to use this to figure out. We're going to use we're gonna parse out the input, right? So as you can see here, we have some question marks, dot, and hashes, followed by a space, and then followed by some numbers. So here the first thing is we're gonna split out I'm gonna call it maybe the puzzle, and then the second half will be the let's see, the group in string, right? This is the line that's split by a white space. And then for the group in string, we are going to have groups by the group in string split by comma. And then for each element, num, we're gonna turn it into a number, right? So groups will be a array of numbers now. Okay, so puzzle is the puzzle input, and puzzle is the left hand side, and then groups is basically an array of numbers. In this case will be 113. So next thing we're gonna do is that, collapse this first. Next thing we're gonna do is we're gonna figure out how many arrangement there is based on this puzzle and based these groups. So how do we know how many arrangements? Well, I'm gonna try I'm gonna create a function first, and basically this function will give me number of arrangement given the puzzle and the groups. Okay, and this one basically we are going to call sum is equal to this with the puzzle and the group. Okay, so we have this. I'm gonna implement this function over here. So how are we gonna do this? First thing is that we are probably gonna know. We're gonna go through character by character, right, from left to right, and then we're gonna basically whenever we encounter a question mark, we're gonna guess it's either a dot or a hash, and if we can, and then we proceed down the rest of the string, and if we halfway through, and then at the end of after guessing out all the question marks, and we realize that this matches the combination that is required for the groups, then we will say we will return this. We're gonna have we'll increment the sum, right? We increment the number of arrangements by 1 by saying that okay, this what we tried is a possible arrangement, and if we run into a dead end, basically we run into an arrangement that does not match this combination, this group's combination, then we return 0, then which basically let us know that okay, this is not a possible arrangement, right? And then we have this and then we sum it up all the possible arrangements. Of course, trying out different possible dots, hashes or dots for all the possible question mark, it can be a huge number to consider, right? Because every question mark is basically 2 different possibilities, and then we're gonna try it out. If this is dot, this is hash, whether it will make out in the end, and if we try out, and if we have, say for example, how many is this? Like say for example, if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we have 9 question marks, then it will be a 2 power of 9 possible range, possible guesses to actually have to iterate through to know, and then we reduce down to see what are the different possibility, which of this is a possible arrangement. That will be too much, right? So as we try to guess, we will also, at every time when we make a guess, we will also see whether this guess is a possible, we will try to as early as possible to determine whether we are going down the path that is impossible. Then in that case, we can have an early return so that we don't really guess up all the possible situations. Example of that would be, for example, if we guess this is a hash, and then we realize that we are having 4 hashes in a row which doesn't match this grouping, then we know that we have the early return, and we only go down the path where this is the only possibility for this is a dot, right? And then we can continue and guess the next 8 question marks, right? We cut half of the possibilities, 2 power of 8 kind of possible arrangements away. So let's see how we can do that. So basically, we're gonna have I'm thinking of having a inner function that we can just calling this to let us know how many possible arrangement. So I'm going to call arrangement, and let's see. Let me think how should I make change this. If it's a question mark, okay, so I think first of all is that because this is a string, I'm gonna split it out into a character array so that we, as we iterate through, we can actually swap out the value, and then so we can modify the array easier, right? So right now, puzzle is a string like that looks like this. And as we traverse through, I want to replace this with hash and then try out whether this is possible. And if it's a string, then we can't mutate a string in JavaScript, then it will be a bit troublesome. So I'm gonna break it into an array, arrays of characters, something that looks like this, right? That looks something like this. Then it will be much easier for me to make this, to basically make changes to the array, to split, to swap out this value to a hash and then check whether this is a valid arrangement, and then try the next character in the array. So to split this into an array, I'm gonna do split. My split, the separator is an empty string. Basically just split out the whole array, split out the string by every character out. So we have this thing over here. Then first thing is we're gonna, as we are traversing down, right? I guess we will need to keep track 2 pointers. One is called the puzzle index, right? And then the second one is, I'm gonna say maybe a group index. So this points to which character that puzzle is, and then this points to which character this group is, and so our result is arrangement 0 with the group index. I think we'll start with 0 as well. Okay, so if I think let's first thing is if the puzzle index is if the current character that we are looking at is let me think. Okay, let's start with some end condition, right? The final ending condition is if the puzzle index is greater or equals to the puzzle dot length, then this is something that we need to handle. We need to determine whether this is a possible arrangement based on the groups that we found out so far, right? And else then there's a few different situations, right? Switch between so else, if we switch between this puzzle and puzzle index, I think we don't need else, because we probably will return either 0 or return either 1, right? Based on the condition. We are gonna come back with this condition later, right? As we slowly build out our logics over here. But for if we are not hitting the end, then basically we can say that now we are checking out what is the current character, right? So if there's 3 different situations, it's either a hash or a dot or a question mark, right? So if we are in a question mark, then we will either guess we will guess whether we are in, we'll make a guess, right? Whether the current question mark should be a hash or should be a dot. So how we're gonna do that is, how do you make the guess is, we're gonna make a change, right? For example, puzzle index is a dot. Right, and then we call the arrangement again with the puzzle index and group index, and so this is dot is this one, guess 1, and then we make another guess, this is a hash, and then this is guess 2, right? And then finally, let's just revert it back to the original state, and then we return. So the arrangement will return us like how many possible arrangement based on the, if we guess it's a dot, and this will give us how many possible arrangement if we guess it is a hash. And then so for this case we will return guess 1 plus guess 2. Okay, so if it's a dot kind of case, then let's see, I think for a okay, so for hashes, what I'm going to decide is we'll just keep moving on. We're going to just keep guessing the arrangement, the index plus 1 and the group index. Okay, so if we encounter a hash, then we just we'll move on to the next index. We're not doing anything. But if we encounter a dot, then basically it's either we have just finished we have just finished a group of hash, which is a group of not operational, like damage. We just go finish, like maybe we are here in a dot, we just finish through an array of a group of non-operational, which is damage springs. Then we're gonna check whether this group of hashes, whether it matches the current group index. If it does, then we still know it is we are good, then we can move on. And if it's not, then which means that actually we should have an early return, because we know that no matter how well we're guessing, with the remaining question marks, we are not gonna form an arrangement that is possible anymore. Right, so here we're gonna check if the puzzle index, the previous one, if it's a hash, then we need to like count how many hashes, how many damaged springs, right? So maybe like we have a count damage springs, and if the count damage springs is not equal to the groups of group index, right? This is the group index, then we need to return early, just say 0, not possible anymore, right? And if it's possible, then we can continue on to see how many what is the possible arrangement moving forward. So it's return arrangement puzzle index plus 1 group index, right? And actually in this case the group index will actually plus 1, because we already know that we have just finished one group, and then the next in future we're gonna check is to check the next group instead. Right, so this will be our situation. So of course we need to count how many damage springs. So while puzzle index greater equal to 0, and okay, hold on, we have the index equals to puzzle index minus 1, while index greater equals to 0 and index puzzle of the index is hash. I'll count damage springs increment and then index minus minus. Right, so we count how many index by looking backwards. You can use a while loop. You can also use a for loop if you like. Sometimes for loop looks cleaner, I guess. Like if I'm gonna rewrite this in a for loop, it will look something like this. For let index equals to puzzle index minus 1, and I guess it's the same thing as well with all this condition coming in, and then index minus minus, oops, and here is the thing that I'm going to do. So it looks cleaner in some sense because everything that's related to the index as the condition and how we're gonna change the index is in the block of the for, and then this is what we actually do inside the loop, which is the count damage springs, right? So it has some cleaner separation over here like this. Also in a while loop you have initialization, you have some condition, and you have the incrementing, so all in like not part of the while loop, so it's a bit spread out, right? So I'm gonna change this to a for loop instead. Okay, one thing to note though, like this itself could be negative because puzzle index could be 0, right? So if puzzle index is greater than 0, right? Oops. If this is greater than 0 and this, then we do this. If it's not, it is neither the case, then we will be having this instead, right? Puzzle index 1 and group index like this. Okay, and sooner or later, if we encounter hash, we do this. If we encounter a dot, we will either early return or we're gonna move on. And then if we are in a dot but the previous one is not a hash, we will move on. And then so the hash case, dot case, and the question mark case, we are done, right? Hey, hold on, this. Okay, so this will call back to itself so that we go back to this case to handle it, right? And once we move on and we move to the end of puzzle index and puzzle.length, in this case, let's see. So when we reach the end, I guess it depends on where what's the last characters we are, because if the last character is a dot, then we basically should already go through all the groups, right? The group index should already be in at the end, like the length of the puzzle of the groups, so that we know that we already checked through all the groups. But if the last character is a hash, then we actually haven't checked whether the last group actually matches the condition or the criteria of the groups, right? So there's two situations. So if the puzzle length minus 1, right? If the last element, or you could do at like -1, it's the same idea. If the last element is a hash, then we need to check the last group. Else it should be a dot, right? If it's a question mark, then we probably will swap it dot or the hash, and then we move on, right? And then we come back again, right? And only a hash and a dot only we can move on to increment the puzzle index, so that we go to that it reaches the puzzle length, right? So this must be a dot, must be a dot. And in this case, if the group index is less than the group's dot length, then which means actually we haven't formed enough groups yet, which means something is wrong, right? We haven't formed enough group yet, which means something is wrong, which means this is not a possible arrangement. Then this should be written 0, or else then we should return 1, right? For dot case, this will be the whether this is a possible arrangement. And we can simplify this by saying that if this case, then we return 0 or 1, right? So it really depends on whether the group is, we are still missing some groups that we haven't formed, we need to form. Right, so this is the case for a dot. And for case for a hash, then we are basically copying a bit of the logics over here that on how we can count number of damage springs for the last group. Right, so count the damage springs. We start with the index equals to the puzzle length minus 1, right? And then we keep decrement, and then we count the number of damage springs. And so if the count damage springs is not equals to the group this thing, right? It's not equals to the group index, then return 0. And if group, so in this case we know that it matches the group index that we currently in, and then so basically, and this the group, right, that we are in, the group index must be the last group, right? If it's not the last group, then something is wrong as well. So if group index not equals to groups dot length minus 1, then also this is not a valid arrangement, because we matches the group looks correct, but then we still have missing groups that is not in this arrangement, then this is not a possible correct arrangement, and else we're gonna return 1, right? Of course, we can also rewrite with ternary expressions to represent this as well, right? You can change that as well, but I'm just gonna keep it as is for now. And I guess that's it for the implementation, right? So let me try and run and see whether we get a correct answer out of this. Let's run node day 12 puzzle 1, and we get 21, which is, in this case, is the answer that based on our example here. So let's go and try an actual puzzle input. This looks like a long huge list. Let's copy this and come back to our code. I'm gonna replace this over here, paste it in, save it, and then let's try run again. We get 7084. Let's copy this. Let's come back and paste this answer in and hit submit. And yes, that's the right answer. We have solved part 1 of day 12, and let's move on to part 2. We have 1 gold star down. Part 2. As you look at the field of springs, you feel like there are way more springs than the condition records list. Oh no. When examining the records, you discover that they were actually folded up this whole time. To unfold the records on each row, replace the list of spring conditions with 5 copies of itself, separated by a question mark. And replace the list of contiguous groups of damaged springs with 5 copies of itself, separated by a comma. So this row, like this, would become this. Okay, so basically whatever we have, it repeats itself 5 times with a question mark in between. And this also repeats itself like this. The first line of the verb will become like this instead. So the first line that we have is question mark dot hash hash hash. This will turn into question mark hash hash hash, and then a question mark, and then this again, question mark, this again, question mark, this again, question mark, this again 5 times, and then 113 will be repeated 5 times as well. So in the above example, after unfolding, the number of possible arrangements for some rows is much larger. So this has way much arrangement than it was previously. Whoa, this is way even more. So after unfolding, adding all the possible arrangement counts together produce this number. So unfold your condition records. What's the new sum of possible arrangement counts? Okay, this looks much more complicated. Let's just try first with the initial example and see whether our code can handle this situation. Let's of course, first is we're gonna duplicate the code to puzzle 2, right? So this is the part 2, and let's copy this and replace this puzzle input with our original one. Okay, and so now the thing is that we can keep this code and see whether it can still run perfectly as it should, but of course the puzzle now is duplicated 5 times, right? So so in group in star, in string, this one, we're gonna repeat itself 5 times, and then this as well repeat 5 times, and right, so both of them repeat 5 times. The puzzle itself, after it repeats 5 times, it still needs to be joined by, it has itself, okay, and then the in between still need to fill in with a question mark, right? So let's make that happen. So let's see. So the puzzle, final puzzle, is equals to, let's see what's the easier way to write this. Okay, I think the easiest way to write this is basically puzzle plus question mark plus puzzle plus question mark plus puzzle. We just manually write all of this out, right? This is basically repeat itself 5 times, split in between you have question marks. I'm gonna cut this, put this in here, and yeah, that basically this is the hold on, let's see, final puzzle equals to this. Okay, right, cleaner. So this will be our code, and let's run and see whether this makes sense. Right, on day 2. Oh no, something is wrong over here. Okay, so same thing goes with here as well. We need it cannot just repeat itself 5 times. It also needs to have a comma in between itself, right? So we will have I think let's quickly create one simple repeat 5 string with separator, right? And then this basically gives us a string separator, no, string new array 5 dot fill with the string, and then join with the separator, right? So repeat 5 for the final puzzle will be puzzle repeat with separating by a question mark, and for this one basically repeat 5 group in string and then join separating by a question mark. Okay, let's try to run this code. Takes a while to run, but we get the answer. 525152 525152, which is correct. And let's try with the actual puzzle input. Hopefully this doesn't take too long. Let's try and see. Let's save this. Let's run this. Okay, it takes a while. It takes longer than I'm expecting. So we need to figure out what's a So I guess we need to figure out how we can make this more efficient, right? Or else it will take a really long time to actually run this through, right? So we need to figure out what is there a way that we can make this more efficient in our code. Usually, like this kind of situation in this kind of code, when we run into when we are trying to figure out different kind of possibility, different combinations, this kind of thing, I guess one thing that we usually need to try out and see is to try to have some sort of try to be more aggressive in the early returns, right? So because for example in this example over right here we have 14 question marks, which means that we have 2 power 14 number of possible arrangements that we have, right? If we have too many, if we have so if we try out all the 2 to the power of 14 arrangements, it will take a while. And now because we repeat it 5 times, then we have over 5 times 14 is we have over 72 to the power of 70 kind of combinations to try it out, and that is impossible to try out all the different kinds of arrangements because it will take forever just to figure out which 2 to the power of 70 arrangements of them which is a possible one just from here, right? So we need to have some sort of more aggressive early returns. We do have early returns whenever we encounter a dot, right? Whenever we encounter dots, basically we'll check to see that the ending group whether it's a possible correct one, and then if it's not the ending group is not possible, then we can end early. But when we encounter a hash, we didn't do that. Okay, so so it's possible that we run out a lot of hashes, like we form a huge group of hashes. Maybe in this case we have all of them, like we have 8 hashes, and then we still have this 2 to the power of we have still 2 to the power of 6 of different combinations, and we check through whether they are valid. But actually all these 2 to the power of 6 of combinations that have this 8 hashes in front is actually invalid, because they are all really run out. We already have 8 hashes, and because this is group 7, this is just impossible, right? So we can have early kind of return whenever we go to a hash. If we encounter a hash, and if that hash is 1 hash is too much than the current group, then we can say, okay, this is not a possible arrangement, that's early return. Right, so we can try that. Let's undo back to our group first. Right, so running with this alone, right, will take us a while, right? You can see that it takes a while before we get the answer. So maybe we try and see whether we add the hash, we still get the sort of like correct answer, right? So this is correct answer, but if we do some early returns, we need to make sure that we are still in getting a correct answer, right? So here, if we end in a hash, we're going to check based on the past hashes, are we actually running up to the correct number of hashes so far, right? So one thing I realized that every time we check the number of hashes that we're running up to, we have to iterate back and look back and count back how many hashes that we have run up so far, right, with this for loop, right? And I think that we can actually have it as a variable and count it up instead, right? So maybe we have this is number of hashes so far, and we start with 0, right? So this is the number of hashes so far, okay? And so for example, if we are running into a dot, right, in this case then we can say that and the previous group is just a hash, then we can check if number of hashes so far is not equals to the groups, then we can have early return already, right? And if it's not, then we can move on to the next one. And since we already encountered dots, then we can reset this value back to 0, right? And if we don't have anything, then I guess we can also pass as 0 moving forward, or we can just pass this on. This should be already reset to 0. If we encounter a question mark, since we are going back to the same index, then we just pass this value on, because we are not counting up or down or reset anything. We are just going back to the same index for this puzzle and then let these two conditions to handle themselves, right? So if we encounter a hash, then one thing we need to do is this: we're gonna increment up, right? And after incrementing up, we need to check whether number of hashes so far is greater than the group index, right? If it's true, then we need to early return. We're gonna say whatever we try out so far is not a possible arrangement, we're gonna return by 0. But if it's possible, then we're gonna continue calling this function, and we're gonna pass this number on forward, right? So same logic as we in the dots. When we're at the end of the group, we actually don't need to count how many hashes so far, right? Because we can just use this value and then do the comparison. So which basically is this part, number of hashes so far. So we don't have to count it up, right? So we can return and save this. And that is the small change that I've made to just quickly count the number of hashes so far. And also we do early returns when we encounter hashes as well. If it greater than the number of groups that we have, that of the current group, then we also early return. Let's try and run and see whether, okay, we still get the correct answer, but whether it's more efficient, I'm not sure. So let's try and copy this actual input. Let's paste this in, let's save, let's run. It still takes a while to get the answer that we are expecting. So right, so I guess we still need to figure out anywhere we are slow and where we can improve our anywhere we can improve our implementation, right? So one possible situation that we might run into is that the number of dots that we have running up so far, one possible situation that we just reduce right just now is that we remove all the possible, we prevent us to running out a lot of hashes and that go into a group that is not possible. Next situation is that we want to make sure that we don't run into a situation where we have too many dots and we don't have enough space for the number of hashes later on, right? So for that situation, we can have an early return based on this condition, right? We need to make sure that every time we are in an arrangement, right, if it's greater than, it's in the final state, but also if based on the group index that we are currently in, we need to make sure that we don't run into a situation that we don't have enough number of springs that we. So let me see. I think let's write it this way. Right. So for example, I might be in this situation, right? I might be in this situation where I have 1 and 3, for example. Am I in this situation where I have decided that all these are going to be dots, and then we are left with like 3 question marks or 3 something, right? I don't know, maybe 3. We are here. We're left with 3 more springs to go through, and then we're not even sure that it's a question mark or a hash or a dot, not yet. But since we're left with only 3, and we have this is our criteria that we need to meet, then we actually need to have at least 5. We need to have at least 5 springs that we have to go through to actually accommodate this, right? Because this is 1 and a space and then 3, right? We need at least 5 springs forward to accommodate our requirement. If we don't have that, then basically we are screwed, right? There's no way to fit in this criteria in only left with 3 springs, right? So basically we're gonna go through the groups. We're gonna go through a groups array, and we are gonna create an array called remaining required. Okay, and this remaining required tells us how many springs remaining required for the current group index that we are currently in, right? So we are in this index, and we don't have enough of the if we don't have enough springs remaining, then we are screwed. We can't possible form this criteria, right? So the remaining required for this case, I'm gonna build this up. We're gonna for loop through the groups. So start with 0 length, and I will have the remaining sum. I'm gonna call it sum. So the first sum will start with groups I. Remaining required I will be equals to the sum, and then I'm gonna add 1 more as a space before I go on next one, and then I loop through, and then as you can see, I'm actually, hold on, I should actually start with from the end of the group. And then this one after. So I'm building up from the end of the group, right? So for the last item of the groups, basically the required is the sum, basically that value. And then when we move from the back to the front, I think this is a bit confusing. No need. I don't think we need a reverse. So we start from the back to the front. So the back and the required groups when we add the last element is basically the value itself, and then so we set it into the remaining required, and then we plus 1 because for the next one we need to have that value plus 1 plus the value of the group, and then we add it to it, right? So this is the array of the remaining required and the index, the element in that for that particular index is basically for whenever we add these special groups that how many remaining we required for how many remaining springs we require to form this kind of this arrangement. So here we are only checking in when we are in index over here, right? So if we are in index, and if I guess here we already know that the previous one is a something, and then we move on. We're gonna move on to the next group like this, right? So before we move on to the next group, we're gonna check whether we still have enough springs to actually form the next group. Alright, so if the puzzle length minus puzzle index is less than the group remaining required for the group index plus 1, then return 0. Right, something like this. I think this is a bit confusing. Let me remove this first, but let me add it here, right? So puzzle length minus puzzle index, if it's less than the remaining required, then we're gonna early return. Let's try and run and see whether it makes sense. It's also very slow. It's not helping at all. What other situation that we can improve? Well, let me copy this thing first to make sure that our code still works. Well, let's collapse this. Let's paste this in, save. Okay, it feels slightly faster, does it? I don't know. Hold on, here. Right, if we don't have this, okay, it's not noticeable at all. But over here, after adding this condition, we're still getting the correct answer. And actually let me print this out to see actually whether this condition is helpful at all. Okay, it does help some early returns over here in our code. So basically, I think we do save some time, some arrangement that is not possible at all. So for example, the length is, so just now the situation is like this, right? So the length is basically we have 7, and then 7 minus the current index we are here is basically we have running up to here 0, 1, 2, 3. We're here 7 minus 3 is 4. 0, 1, 2, 3. 7 minus 3 is actually 4. 4 is actually including itself. I think we can minus 3 minus 1. I'm always confused by this kind of off by 1 kind of situation. So this is minus puzzle index minus 1, and then less than the remaining, right? So 4, we always have to less, okay, so it's 3, and less than remaining, right? So remaining required is probably we need 5 required, more than is less than that, we can't make it, right? If the current group is 3 and then we left with 3 more, then I think we can still make it, right? So less than is correct. Let's run this, right? Can't really tell whether it's improved much or not. I think we also need to add this over here as the logic over here. But because this one, we decided that we are going to move on one more group, right? Then I guess remaining required should check with the next group instead, right? So I have this condition like this. Let's run. So you get the same answer. Can't really tell whether it's faster or slower. So we are going to put back the. I feel like the. Let's see, I'm not sure that repeat 5 here is something that we want to optimize, but I feel like it's probably not much of a difference, but I decided to do so anyway. So we have arrangement, we have an array instead of the string, and then we're gonna have the separator. And what we're gonna do is that instead of repeating the string, we create a string that repeats itself 5 times, that splits separate by a separator. We're gonna call the repeat 5 with the final array that looks like over here like this, right? So repeat 5 with this one instead. Oh, hold on. It should be the puzzle split by empty space. So we're going to repeat the array instead. So this is the same thing. The group in string split by comma, map to number, and then repeat 5 is repeat the array instead. Okay, so in this case, repeat 5 we have this we don't have any separator because we just need to repeat the number 5 times. So this is the result array, and we are going to loop 5 times. Return the result, and every time for let j equals to 0, j less than array length j plus plus, we're going to push the array j, and then the end, every turn if we have separator. If separator and I less than 4, right? 1 2 3 0 1 2 3. I'm going to push 5 times, not the 5th time, not the last one. If it's less than 4, I'm going to push separator as well. Let's try. Not much of a difference, but we still get a correct answer. So I guess we've made this change as well. I guess we still have to figure out any aggressive way of improving or early returns that we can add into this one. I think this part we probably don't have to worry too much, I guess, for now, because we tried out either this or this, and then we go in and then we have basically an early return every time when we are in a dash. We have other conditions to make sure that we hit early returns, right? Like here, like all these different kinds of conditions. So I think we can still focus on just this part over here. And reach the last group. Yep, that's so let's still run this through with the actual inputs, and let's see how slow actually it takes, right? Oh, okay, I think let's do it this way. Let's print out line by line and then see which line basically takes the longest, or which line we actually takes a while, right? So console log line, and let's run through. So this line basically is we stuck here for a very long time. Okay, as I said here, right, 7.2. Okay, we managed to go through, and then this one again with a long list of a question mark. This is basically a question that we will stuck for a very long time, right? Because basically this one has how many? 2 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 question marks, and as 14 times 5, we have basically 7 and 2 to the power of 70 kind of combinations that we have to go through to basically count out how many possible combinations, possible arrangements that we can make, and that is why it is so slow, right? So while it's running through, we are still very far behind, I guess. Our line at 24, and we have thousands of lines. It will take a while. Let's think about it. How can we improve this? So let's think about other early returns that we can possibly have, right? Maybe in this case, right, we can already fulfill the condition of question mark dot, right? Then basically we don't have to go through the every time we actually every time we want to try a hash, number of hashes so far. Let's kill this and let's try to focus on this particular case, right? I think the 7.2 case is something that will take a while to run. If we may make it fast, then I guess we can improve our code, right? So this 7.2 case, just copy this, let's just run this, right? It takes a while to run. It has a lot of question marks. So let's think about our early return kind of logic, right? So okay, so maybe we can already form 7.2 early on in the game, right? And then the rest of it is question marks or either or question marks or like dots, right? And basically we can know that we can skip ahead. We can decide early on that actually we don't have to this is a possible arrangement, and the rest we can just any question mark should just treat it as dot, and any dot we just treat it as dot. But if we have a hash at the end, then we know that basically this is not a possible arrangement. We don't have to even go through at the end of the list, right? We just need to know whether from this index onwards, is there any hashes left behind, right? So basically, this means that when we are here, right? Basically, when we are here and we're ending, we are gonna move on to the next group, right? This is basically the only time we're gonna go for the next group is we're not moving on to the next group over here, right? Only time is when we have a dot. We're concluding the current groups, and we're moving on. Over here, we basically check if this is the last group, and if it's last group, we need to check whether the rest of it, we are not going to see any hashes. If we're going to see any hashes, this is not a possible arrangement, right? This is not possible. But if we're not seeing any hashes, then it's just question mark and dots, then we say actually this is it as well. This is just one possible arrangement. The rest of the question mark has to be just dots. And if it's just rest of it is just dots, then it's also that's it, right? This is just one possible arrangement. There's no need to just check out any other possible arrangements, right? So in that case, we need to have another arrays again. I'm gonna say this is called a hashes remaining. Goes like this, and this array basically is based on the puzzle input index. So I'm gonna say let I equals to puzzle length minus 1, and I equals to a greater 0, I minus minus, and same thing, some start with 0, and hashes remaining for the index is equal to sum, right? And if puzzle I equals to hash, then sum plus plus. Okay, so I think this either up or here, down here, I guess it doesn't really matters, because the time when we check whether the hashes remaining is we are on a cell that is a dot, right? And we check any remaining hashes from here onwards, right? So how I'm going to use this is that when I need to go next, group plus 1, if group index is already at the end, so group plus 1 is already the group's dot length. In this case, we are at the last group. Then I'm gonna check if hashes remaining in the puzzle index is also 0, right? If it's 0, okay, so if it's 0, no more hashes, then this should be the only arrangement. If it's not, return 0. This is not a possible arrangement, right? So basically here we can actually do this. This is either 1 or 0. Okay, like this. Let's see whether it makes it faster. Not quite. Hold on, I think it's slightly faster. I don't know. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so roughly 8 seconds. And if we have this early on, 1, 2, 3, 4. Okay, it's much faster. It's like 2 times faster. Okay, so it is promising. Let's skip this and let's see what else we can improve on, right? So let me think. So here we are getting the same number, right? It is. I assume this is a correct answer. What are the possible situations that we can early return? This is so far. I think I can't think of any for now. Let's paste back this original, and I feel like we are making good strides. It's take a while, but it should be much faster than it was, right? We are moving forward. So this situation, this is also a hard one, right? So this can have two ones. Okay, I guess like if we are having a lot of hashes, but still, let me think what other things that we can improve on over here, right? So, but this is quite fast, I remember just now. But the slower ones are like we have a bunch of these question marks, and we need to form like 191, right? So and whenever we actually run into a like 1 9 and then 1, and of course we can have a lot of dots, right? But then once we hit like we can have too many dots until so we were trying out dots at the wrong time, right? Oh, okay, if we try out dots at the wrong time, basically have already early written. And if we try out I guess this is to try out, this is to, let's think about, because we repeat ourselves 5 times, of course it makes it, makes more possibilities, but is there something that we can actually repeat or like times 5 the number combinations, right? That's something I'm thinking. Like, is there something that we can have 5 times the situation, right? Where are we right now? We are still far along. We are still in here. 41111. This is row 50, right? By the time we hit 1,000, I guess you will not want to tune in. But let me think how we can improve. What is the possible early returns over here that we can do? Like this is 4. We can have dots, 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 dots. Okay, we cannot have too many dots in front, right? Once we hit 6 dots, then we know that anything we try on, right? Basically this. Anything we try on, it's impossible arrangement, right? But we still want to try dot. Like if we have all this as dots, we still try out like dots, 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 hash, hash, dots, hash, hash. We still try out like 2 to the 3 combinations before we hit here. We realize that actually we are in a path of doom, but we actually have tried out 2 to the power of 3 combinations. Is it that bad? I guess it could be worse if we are in here in a situation where we have two dots, two question marks, and then we try out we're in a situation where we realize that we still have that we don't have enough space to actually try out like a 4, right? And I guess like this is hard, particularly hard because you have a lot of space to do the ones and you have different combinations of ones. Is there something that we can actually memorize, right? For example, if we realize that we have completed and then we left with 2 ones, we know that this is how many combinations that you can make. There's something that we can do, but it's not that straightforward though. Like if we have repeating this 5 times, that looks like this. Are we able to tell where the ones is gonna be? Right? A bit hard, right? I mean, this could be the 1. This has to be the 1, right? A. I guess like if we are able to come here, if we decided this is 1 and the next group we are going to look for is a 4, we can skip through all here and start trying a 4 over here, right? But how many combinations are we skip through, right? But basically we only go through like 1, 2, like we are going just going down all the ones, right? Of course the question mark, okay, let us try out hashes, but like this is 4, 16 combinations, 2, 4, 8, 16. So we'll waste 16 combinations that we realize that it's not possible. Step back and then we start trying out again, right, before we go and waste another 16 combinations over here. But is 16 a lot? Should we cater a situation where maybe before we try the hash, let's see whether it's actually possible to reach form 4 of it. Do we have enough of it to form 4? Right? I guess that's something that maybe we can think about to optimize, and then we realize that it's not possible, then we can have an early return. Right, okay, let's try that. Let's kill this since we are kind of stuck in this case now. Right, so this is the case that we want to look at, and basically this is the case that it will take quite long. I realize that it takes more than 10 seconds for this one, right? If we can optimize this, I guess it helps for other situation as well. Hopefully it helps for other situation as well. So I thought this would be an easier case because it has 1, 1, 1, 1. So it feels like it's much easier to consider than the 7, 2 kind of situation. This a group of question mark kind of situation, right? But apparently it's not. So let's see. So first of all, let's see. First of all, we need to do some pre-runs and prepare some data structure that we need to let us quickly look up to know that whether at our current location, if we try to hash, are we actually able to form the group with the remaining hashes or question marks that we have before we hit a dot, which tells us basically if we are here, we are starting this. If this is the first hash that we're going to try, this is the first hash that we're going to try, I'm going to look up and see whether we have enough runway to hit 4 by basically looking up where is the next dot, right? By finding out where is the next dot. Okay, so let's just look at this and let's focus on where we are. Right, so okay, I think first thing is I'm going to have an array that tells us when is the next dots that we will see, right? So I'm going to call it next dot index. And again, this is based on the puzzle length. And I guess the sum is the distance. I'm going to call it the, yeah. Let us, sum is the next index. And next index is actually going to be the puzzle dot length, right? So basically, if you are in the last position, next dot you're going to get is puzzle length. And okay, so here puzzle next dot index of the I is equals to the next index. And if this is a dot, well, let's say the next index is I. Okay, so let's print out this and take a look next dot whether we build out the array correctly. Oops, hold on, I have an error. Oh, hold on, is this one? Right, so the next for this one, starting from here, the next one is at index 12, right? This is, yeah, index 12. So all of them is index 12 until we reach here, and the next one is index 15, 15, 15, 15. Okay. So now whenever we are in a range, okay, when we are in with this one, with the hash, okay, so this one checks if we have too many hashes for the current group. Next one we're going to check if we have any enough spring to form the current group. Right, so for example, if we are in the hash, so number of hashes so far is, say for example, now we are in this situation, hash question mark dot. Okay, so for example, we are in this situation, we already have 1 hashes, number of hash is equals to 1. Our index is currently at 0, and then the next dot is actually 0, 1, 2, 3 at 3. And then, so basically based on our group, right, what is the group size, right? So if our group is I'm going to say next dot is 3 minus 1, so our runway is 2 more. We have 3 minus 0 minus 1. Okay, so for example, if next dot index of the current puzzle index minus the current index, right? So the next is 3 minus 0. Over here we have 3 more rooms to go. This 3 room, if it is less than the requirement for the group, so it's a group index, minus the number of hashes so far, minus 1, because don't count the current one, because this counts the current one, so minus of the current one. And if it's less than that, then I guess we can say we can return 0. Okay, adding this additional condition in. And I'm gonna print some logs to see whether we hit this condition. We do hit this condition, right? I guess it. So which actually means this condition is quite useful. But well, hit this condition way more than I expected. So we're actually saving up quite a lot of unnecessary conditions, right? But still, we are not getting our answers out from this puzzle, right? It is not as straightforward. It takes long. It takes a while. So what are the things that we can optimize for this one? Hold on. Before we keep running this, let's make sure that with this we are not running into a wrong answer, right? So let me check with something like this one. Okay, for this one, if we don't have this is 32, right? And we have this, and we have some early return. Check the early return. Right? We don't hit early return at all. 1, 2, 3. But if we hit dot, I thought we would hit this anyway. Hold on. Gonna be not hitting this at all, right? What if we try 3 dots in front? Then we will basically have to come in here and realize that this is not possible. Right, so hold on, let me print this out. Hold on, I think I want myself to be at. That's too many logs. Okay. Let's just focus on this one, right? I feel like after 3, 0, 1, 2, 0, 1, 2, 3. If I'm at index 3, if puzzle index 3, I want to check out what are the possible next dot index that I have. Next dot, and then the number of hashes so far, and also the group requirements, So when I 0, 1, 2, 3, next dot is 5, right? Number of hashes so far can be 1 or 2 or 3. The requirement of the group is 3. Hold on. So in this case, zero, 1, okay, let me copy this out first. So I am, yeah, it should be, so 0, 1, 2, 3, I'm here, right? And the number of hashes so far is 1, which is, this is the first one. I have 3 dots in front. Then my group requirement I want to have is 3. And the next one is at 5, right? 0, 1, 2, 3, 4, 5. 5 minus, this is 5. 5 minus the index. 5 minus index is 5 minus index. 5 minus 3 is 2, right? We're left with 2 places so far. So this is 2, and the group that we want to form is 3. So 3 minus number of hashes so far is 2, and 2 minus 1 is 1. Hold on, something's 2 minus 1 is 1. No, this one. We left with 2 places. We left with, we have 2 slots. Oh, this should be plus 1. Groups minus number of hashes so far, 5 minus 1, left with 2. 3 minus 1 left with 2, but actually we want to form 3 plus 1 back, right? So, okay, this should be 3, and then this should be 2, and then 2 is less than 3. Okay, I guess this makes more sense, right? So we have more situation that we print out that is invalid. Okay, as this gives us more early return than we want. Let me comment this, remove this. Let's try back the previous one, which is the harder one. Where are you? This one. And see whether this logic helps with this case. Still does not help that much. Oh man, why? What are the things that we can improve? This whole logic, this is... Okay, I think one way to see here and see where we can improve is we are going to print out the different kind of combinations that we have formed so far, and then we're going to see like where we are stuck at, where we are trying out, where actually that is down the path of sort of like doom, that situation is it's not possible, right? So what I'm going to do here is every time we're going to go for arrangement, I'm going to print out the puzzle.join plus space plus the group index plus the puzzle index, right? Let me just use the template literals, much easier. Puzzle index and group index. try and see. Whoops. Okay, so here we are at the very last leg, right? Actually, we're at the very last leg and we keep trying out all the different possibilities, and yeah, it's just that there's a lot of possibilities with ending with 111, right? And these are all valid kind of case. I guess that this basically tells us that there's room for doing memoization. Actually, it is possible to do memoization, especially at the end of it, right? Let's try and see whether we can memorize anything, right? So if we are at if we're at this particular stage, at this particular index, right, I see 8221 in this case, right? If I try to copy this happens a lot, right? 8221, 8221, and when we are at 8221, basically we're at index 82 and we are in group 21, we know what's the results, right? Right, yeah, and we have 8824 appears a few times, 8221 appears again. So they are actually repeating, kind of get the number at the same kind of index. So you're trying to store these results, right? 8221, then basically we save our time to go down, like to trying out like what are the possible values based on the 8221. What are the results for the 8221? So now we're gonna, after seeing that it actually repeats that much, we're gonna do some memoization. So here I'm gonna create a memoize map. I'm gonna say memo, and the key is actually gonna be key is based on the puzzle index, comma, group index. And if memo key, if the answer is already in the memo, then we're gonna return the answer immediately like this, right? If not, then we're gonna run through our logic, but here we need to know what is the we need to update this value as well, right? And we need to go to all the return statement and do that. Feels like it's a bit troublesome to do that, to be honest. Let me see, there's so many early returns and we need to cover all of the early returns if possible, right? I think that's quite a hassle. So what I'm going to do here is actually we're going to create another function called memo arrangement. Basically gonna group index, number of hashes so far. So actually this has 3 inputs, so actually I should have the 3 of the inputs to be the part of the key, right? And this returns this one, right? If not, then we're gonna call arrange the result gonna be arrangement with the puzzle index, group index, and number of hashes so far. So this, we're going to call this value this results, and we're going to return the result, but at the same time we're going to store it in our memo as well, result, right? Here one thing we need to make sure is that the arrangement itself shouldn't call arrangement anymore, should call the memo arrangement. I'll replace them, right? So so that the subsequent internally in the arrangement we're gonna call with the memoized version. Right, so no more, and of course this one we'll call the memoized version instead. Okay, let's save this and let's try and run. Way to go! It's much faster. We should have solved this with a memoization early on. I guess that will solve a lot of edge cases that we don't even need to figure out whether we should early return. Anyway, let's copy this whole thing. Let's come back. Let's paste this in. Let's run. Okay, we're still plowing through. So not all situations can be solved with memoization that fast. I guess it also still takes some time to solve some of the trickier kind of situation. I wonder why this takes longer and it wasn't flagged out early on previously. Or is it because we couldn't solve until this question? No, right? Okay. This is something we need to... Where was it again? Remember, it's like a 1311 kind of question. But we'll take note of that. This is also slow. Let's take note of this. We're gonna figure out how to improve this one. 1, 3, okay. But I guess we are moving faster now. Or have we? So this one is solved easily, right? So this case 13142. Not easy, right? I guess we need to figure out whether is there any early returns that we can do for this one so that we can run faster. But let's see the memo arrangements. Okay, anyway, we get our answers now. At least now this is much faster than it was previously. So if you have any great ideas about how to improve some of the edge cases, let me know. But I'm gonna submit this answer since we get it within 2 minutes. And hopefully it's a right answer. Oh my god, this is not a right answer. The answer is too high. If you are stuck, make sure you use the full input data. Okay, sure. Wait, why is that so? Okay, so hold on. Just make sure that we still get the correct answer so far, that based on our previous input after we make all these changes. Right, so save this, I'm gonna run this thing. And okay, we are not getting the right answer anymore. So must be some logic that we added that make it incorrect, right? So could it be the memoization? Let me see. So if I try to not doing any memoization, okay, so okay, I guess it's the memoization, but something is wrong with the memoization that causes the issue, right? So parser index, group index, number of hashes so far. If in the same right parser index, group index, and number of hashes, should be getting the same value, right? Arrangement, we are not doing any. Oh, there's side effects, right? There's those. There is side effects of that we call this arrangement with a certain puzzle index and group index because of this one, right? We call it 2 times, it should be getting different answers. So okay, so the memorization, I'm going to change a bit, right? So not all I guess you should also memorize based on what the current value is, right? If it's a I guess let's add the current value into the key, and maybe that will solve the issue. So the puzzle index. Save this. Let's run. Okay, so now we still have our memorization on, but we get back the correct answer now, right? So let's try and run with the actual input. Let's see whether how is things going with this one. So now this is slow again. So let's save this. Okay, we are making progress, I guess. So this is also a slow one, right? But where was I guess just now we were stuck at the 41111. Can't remember where was it now. Where's the 4? Or have we not reached there yet? Oops. 1114 is also slow. This is 182. This is 56, so we actually passed 56. So actually we that is not a blocker anymore. But questions like this is still a blocker. Let's just wait for a while and see whether we can break through. I guess now with the memorization based on the current value, if we have more question marks, then we actually have more the memorization of it will be different, right? But actually we also memorize the question mark. Okay, so we actually get it through. So there are just a few hard questions that we have, but nonetheless we also spent roughly 2 minutes to actually get it done. And hopefully this time round we get the right answer. Yes, finally, with all the early returns, all the pruning, all the logics, optimizations that we add on, and also finally, I guess the most important one that improves way much more is the memorization, right? So after all this, we managed to get our answers within 2 minutes and a half. Takes a while. I guess there are still rooms to think about how we can optimize our solutions, but nonetheless, we still managed to solve our puzzle for day 12, part 2. And that's it. So we're gonna see you in the next day, which is day 13. So see you in the next puzzle. Bye bye!